The definition of a second-order linear homogeneous differential equation is a sub 2x, the second derivative of y, plus a1x y prime plus a sub 0x y equal to 0. Assuming a sub 2 is not 0, you can get a standard form for this differential equation, which is the second derivative of y plus px y prime plus q of x times y equal to 0. Also recall the definition of ordinary and singular points. For a second-order linear differential equation, a point like x sub 0 is called ordinary point if both px and qx are analytic at that point. What's the meaning of being analytic at that point? It means that they have power series representation. Basically, wherever you see polynomials, then they are analytic at any point. Any point that is not ordinary point, we call it a singular point. What's the importance of ordinary points? We have a theorem saying that, hey, if you have a differential equation around ordinary points, you can find power series solution. So suppose you have this differential equation, the second derivative of y minus xy is equal to 0. Any point is ordinary point. So basically, using the theorem, we can find power series representation around any ordinary point. Let us follow the ordinary point 0. Our goal is to find power series solution for this differential equation centered at 0. Let's rewrite the differential equation, and our goal is to look for solution in the form of power series centered at 0. A power series can be written as c sub 0 plus c sub 1x plus c sub 2x squared plus the rest of the terms, or in compact form, you have the summation of cn x to power n and start from 0 to infinity. So a starting index is 0. If you take the derivative term by term, the derivative of c sub 0 is just 0. So the derivative of the rest of the terms can be written as you can see here. The derivative of c sub 1x is c sub 1. The derivative of c sub 2x squared is 2c sub 2x plus the rest of the terms. Or in compact form, you have the summation of cn times n times x to power n minus 1. And please pay attention, and starts at 1 now. If you take the second derivative, the same process, the derivative of c sub 1 is equal to 0. The derivative of 2c2x is 2c2. The derivative of 3c3x squared is 6 times c3x plus the rest of the terms. Or in compact form, you have the summation of cn times n minus 1, x to power n minus 2. And please note that the power series start at 2 now. Okay, so let us rewrite our differential equation, and what we have so far. The second derivative of y is 2c2 plus 6c3x plus 12c4x squared plus the rest of the terms, which in compact form is the summation of cn times n minus 1, x to power n minus 2, and n start from 2, minus x times y. But what is y? Y is c sub 0 plus c sub 1x plus the rest of the terms. So you can write this guy as minus x times the summation of c sub n, x to power n, and n start from 0 goes to infinity, and both of these are equal to 0. Your goal is to combine these two power series. First of all, copy down the first power series. The second power series can be written as the summation of cn x to power n plus 1, and on the right-hand side, it's equal to 0. Basically, if you distribute x into parentheses, you're adding 1 to the exponents. or combining x and x to the n gives you x to power n plus 1. So we have our differential equations, and then we have the power series, which is written like this so far. If you write the first term of the power series on the left-hand side, you get 2c2 x to power 0 plus the rest of the power series, which is the summation of n minus 1, cn x to power n minus 2. And please pay attention. Now the index is at 3. The second power series stay the same, the summation of cn x to power n plus 1, and start from 0 to infinity. It must be equal to 0. Our goal is to combine these two power series, but the first power series start at 3, and the second power series start at 0. So we have to shift these two power series a little bit. How do you combine these two power series? By shifting and using dummy variables. So for our power series, so far we saw that we have the following combination. And we wrote down the very first term, so we can make necessary adjustment in the index and the exponent of these two power series. The first power series start at 3. The second one start at 0. The power of the first power series is n minus 2. And the power of the second power series is n plus 1. So let us take k to be n minus 2 for the first power series, or wherever you see n, you're going to write down k plus 2. Your first power series becomes the summation of k plus 2 times k plus 2 minus 1, or k plus 1, times c sub k plus 2, and x is now to power k. And please pay attention. N started at 3, k starts at 1. Okay, let's see what we can do for the second power series. If you take k to be n plus 1 for the second power series, or wherever you see n, you're going to copy k minus 1. The second power series becomes the summation of c sub k minus 1 times x to power k. And now k starts at 1, goes to infinity. Okay, so far we have the same starting index, k is equal to 1, and you have the exact same power for your x. You set it equal to 0. You are allowed to combine these two power series. So let's see. When you combine these two power series, the very first term is 2c sub 2. The combination of these two power series gives you k plus 2 times k plus 1 times ck plus 2 minus c sub k minus 1 x to power k equal to 0. First of all, the constant 2c sub 2 must be equal to 0. So it gives you c sub 2 equal to 0. Then you take this recursive quantity and set it equal to 0 as well. Okay, what are c sub i's? Your goal is to find the relation between c sub i's, so you can simplify this power series. By doing a little bit of algebra, c sub 2, k plus 2 is c sub k minus 1 divided by k plus 1 times k plus 2. You officially brought c sub k minus 1 to the other side, so you have k plus 1 times k plus 2 times ck plus 2 equals to ck minus 1, then divide both sides by k plus 1 times k plus 2. Perfect. So we have our differential equation, and we saw that c sub k plus 2 is equal to ck minus 1 divided by k plus 1 times k plus 2. Also, note that 2c2 is equal to 0, so c2 is indeed equal to 0. So let us begin. Let's plug in k equals to 1, and you get c sub 3, which is equal to c sub 0 divided by 2 times 3. If you plug in 2 for k, c sub 4 is c sub 1 divided by 3 times 4. If you plug in 3 for your k, c sub 5 becomes c sub 2 divided by 4 times 5, but c sub 2 is equal to 0. This guy disappears. What if k is equal to 4? When k is equal to 4, c sub 6 is equal to c sub 3 divided by 5 times 6, or we already know what c sub 3 is. Wherever you see c sub 3, you're going to use c sub 0 divided by 2 times 3. So just substitute this guy here. So you have c sub 6 written in terms of c sub 0. What if k is equal to 5? C sub 7 becomes C sub 4 divided by 6 times 7. Now you see what are we talking about. C sub 4 already is written in terms of C sub 1. So wherever you see C sub 4, you're going to substitute that by C sub 1 divided by 3 times 4. So you get this quantity for C sub 7. What about k equals to 6? C sub 8 becomes C sub 5 divided by 7 times 8, which is again 0. Why is that? Because you have C sub 5. C sub 5 is 0, so wherever you see C sub 5, you plug in 0. This quantity vanishes, so C sub 8 is 0. With the same argument, plug in 7 for your k. We are all using this recursive relationship. When k is equal to 7, C sub 9 becomes C sub 6 divided by 8 times 9. But what is C sub 6? I already calculated C sub 6, which is just right here. Wherever you see C sub 6, plug in that quantity for C sub 6. So that's how you write C sub 9 in terms of C sub 0. So every coefficient can be written in terms of C sub 0, C sub 1, C sub 0, C sub 1, and some of them are equal to 0 as well. If k is equal to 8, C sub 10 is C sub 7 divided by 9 times 10. But what is C sub 7? You already know C sub 7 is equal to C sub 1 divided by 3 times 4 times 6 times 7. So substitute this guy here and write C sub 9 in terms of C sub 1. Very well. So for this differential equation, finding power series solution is y equals to C sub 0 plus C sub 1x plus C sub 2x squared plus C sub 3x to the third plus the rest of the terms. This is a power series in general form, which in turns can be written as the summation of C sub n, x to power n, and n starts from 0 goes to infinity. Perfect. So y can be written as C sub 0 plus C sub 1x plus C sub 2x squared plus the rest of the terms. We need to plug those in, and we get C sub 0 plus C sub 1x plus 0. We already know C sub 0 is C sub 0. C sub 1x is just C sub 1x. C sub 2 is 0, so this term becomes 0. C sub 3 can be written as C sub 0 divided by 2 times 3 times x to the third. The rest of the terms as well. C sub 4, x to the fourth can be written as C sub 1, 3 times 4, x to the fourth. C sub 5 was 0, so you get a 0. For C sub 6, you get the quantity C sub 0 divided by 2 times 3 times 5 times 6, x to power 6. For C sub 7, as we saw in previous slide, it is c sub 1 divided by 3 times 4 times 6 times 7, x to the power 7. We saw that c sub 8 is 0. Then c sub 9 is c sub 0 divided by 2 times 3 times 5 times 6 times 8 times 9, x to the 9th. And finally, what we saw is we have c sub 10, which can be written as c sub 1 divided by 3 times 4 times the rest of the numbers times x to the 10th, and c sub 11 is just 0. So let's see, what do we have? So far, we saw that the power series representation in expanded form is nothing but c sub 0 plus c sub 0 divided by 2 times 3x to the 3rd plus, we are grouping these together, c sub 0 divided by 2 times 3 times 5 times 6x to the 6th plus, you're basically writing all of the c sub 0 terms next to each other plus the rest of the terms, and then group c sub 1s together. You have c sub 1x plus c sub 1 divided by 3 times 4x to the 4th plus the rest of the terms that are including c sub 1. So you can group these together, everybody. Very good. So what does it tell me? It tells me y can be written as c sub 1 multiplied by some terms plus c sub 0 multiplied by some terms. So you have c sub 0 times, you have 1 plus x cubed divided by 2 times 3 plus 1 divided by 2 times 3 times 5 times 6 multiplied by x to the power 6 and the rest of them. So basically, we took this and factor out c sub 0. For the second one, we can factor out c sub 1, and you get x plus x to the 4 divided by 3 times 4 plus x to the 7 divided by 3 times 4 times 6 times 7, and so on. So basically took these terms and factor out c sub 1. Very good. A lot of algebra. So far we saw that we have c sub 0 times some terms plus c sub 1 times some other terms. y1 is 1 plus x cubed divided by 2 times 3 plus x to the 6 divided by 2 times 3 times 5 times 6 plus x to the 9 divided by some multiplication, which can be written in compact form as 1 plus the summation of 1 divided by 2 times 3 times 3k minus 1 times 3k x to the power 3k. This is your y1. Now for y2, you saw that you have x plus x to the 4th divided by 3 times 4 plus x to the 7th divided by 3 times 4 times 6 times 7 plus the rest of the terms, which in compact form can be written as x plus summation of x to power 3k plus 1 divided by 3 times 4 times 3k plus 1. Very good. We found y1 and y2. And then if you compare it with popular power series, we don't see any sine, cosine, or exponential, or something similar to what we saw before. So it means that even though we found power series, it's not exactly representing the well-known or famous power series that we saw before. We leave the solution as we see it here.